last lecture in this class. And so we talked about free probability theory, and in the last lectures I showed you how free probability theory can be used for getting information about von Neumann algebras, in particular the free group factors. And so we looked on the compression of the free group factors and saw that they are related. So compressing the free group factor with another free group factor. And so those were the first results about the free group factor since the early works of Murray and von Neumann. Okay, and today I want to give you some more ideas what free probability can do on von Neumann algebras. So I mean, this will just be very high-level survey. I mean, the technical details are very tough. No? So I mean, what we did last time, maybe I also did not all the details, but in principle you should be able to fill in what I left out. No? But today I think you will not be able to fill in what I'm leaving out. So I want to give you some ideas of some other applications, maybe also a bit more recent work. So this is some more operator algebraic applications of free probability. And so the main idea behind those applications is what we saw in these asymptotic freeness results, that we can use random matrices or matrices for modeling specific von Neumann algebras. So we can approximate in star distribution the generators in our von Neumann algebras. So this means we have a sequence of matrices which converge in our kind of distribution, in our kind of convergence, namely convergence in distribution, which converge to the operators on our Hilbert spaces. Okay, and of course the idea is, I mean, matrices are quite easy to understand. We know more or less everything about matrices, and the hope is that, I mean, this knowledge goes over under this convergence to the limit. Of course, it's not as easy like this, because operators on Hilbert spaces are much more complicated than matrices, but still we can try to hope some things. The problem is, of course, that our notion of convergence in distribution is quite weak. So we know, I mean, all the properties of the von Neumann algebra are determined by the star distribution, let's say, of generators with respect to a physical state. So we know everything if we know the distribution of generators, but this convergence usually is not continuous with respect to the interesting properties. Okay. So this means it's not just automatically that properties go over. But I mean, still, a lot can be done with this idea. And I want to tell you essentially two maybe big results rely on this philosophy. So maybe first let me call this again, what I just said, down. So the asymptotic freeness results for GUE, and the fact that they converge to distribution to free semicirculars. So they tell us that we have many matrices which converge in distribution to free semicirculars. Okay, so what we showed is that we have a convergence in the average sense, but I told you we also have this in the almost sure sense. This can be strengthened to the almost sure sense, which means almost surely those matrices, the Gaussian random matrices, converge to free semicirculars. And this tells us we have many matrices which converge, tuples of matrices which converge to a tuple of free semicirculars. Semicirculars. And the free semicirculars are generators of the free group factors. So generators of free group factors. Okay, this gives us at least the hope that we might be able to transfer results about matrices to operators. For example, to the free group factors. Okay, and that's actually the case, and some of the most spectacular results of free probability theory rely on this. Okay, and so I want to show you a few of them. So maybe here are results which can be proved by this idea. And so it's a result about, okay, more general for Neumann algebras, but let me formulate them with free group factors. With free group factors. Group factor n of n for n between 0 and infinity. So in this case, infinity is excluded. Not everything is clear for infinity, but for the other one, it's okay. And you can also take the interpolated one if you like, not just the integer n. So we know a few things, okay, which maybe I won't say so much at the moment, but I will explain them. So first of all, the free group factor does not have property gamma. I will explain what this is. And this is not so exciting for the free group factor because this was already shown by Murray and von Neumann. But maybe the second one is that it does not have Cartan subalgebra. And this is a very spectacular result by Roland because there was a conjecture around that every 2-1 factor has such a Cartan subalgebra. And then in the same spirit, building on the same ideas, in G, proved to be a little bit later, and the free group factors are also prime, according to the tensor proposition. Okay, so maybe let me make a few remarks, also explaining what this means. And then I will give you a very rough idea how to prove this one. I mean, this is maybe this is not the most spectacular of the statements, but at least the proof of this is maybe a bit easier to the other ones. Also, I will talk about this, but the idea is the same for all of them. Okay. So here are a few remarks. So first of all, this is, I mean, the proof I will give you is via this idea here, but this result is actually due to Murray and von Neumann. So this is not really a new result. But actually, I mean, this theorem is true for more general, not just for the free group factors. So in this case, it might still give you something. But for the free group factors, it's not a new result. So one is an old result. Von Neumann. I will talk a little bit about the proof, and this illustrates the methods. And actually, this is this property gamma was introduced by Murray and von Neumann to distinguish the hyperfinite factor from the free group factor. I told you that they showed they are not isomorphic, and it's exactly this property which does this. But okay, so 2, this is much more spectacular. This is spectacular result of Roland from 1996. So maybe the most important result about von Neumann algebras coming from free probability theory, and because it was somehow a conjecture that every 2-1 factor has a Cartan subalgebra. Okay, Roland showed no, the free group factors don't. So this conjecture is open by the way. So it was conjectured. Okay, I mean it's not really important for us what the Cartan subalgebra is, so maybe let me just say it in words. So it's a maximal abelian subalgebra of my von Neumann algebra, which has a special property, namely the property that the normalizer of this generates the factor. And the normalizer are the unitaries which have a special property. Okay. I mean, I'm not really going to talk about this, so it's not maybe not really important for us, but it's a special, it's an important kind of object in the theory of von Neumann algebras. Okay, and so part 3, this was then proved a few years later by Living G, was using similar ideas. So this is this slide. From 98, and it says it's primeness. Of course, prime means it's an object which cannot be decomposed into smaller components, like the prime numbers. And this decomposition is with respect to the tensor product structure. So not being prime means that our free group vector cannot be written as a tensor product of two other two vectors. Cannot be written as one tensor and 2. Maybe here we take the von Neumann algebra tensor product, well established notion of von Neumann algebras, for one vectors. This is also a quite important result. So it shows that those factors are really building blocks when you figure things. Good. Okay, but so the only thing I really want to say a little bit more is part 1. So okay, I will tell you now exactly what property gamma is, and then I will give you some idea how we can use this philosophy approximating the guys in our von Neumann algebra by finite dimensional matrices, how this is. Okay, maybe before I give you the formal definition, maybe let me just recall that this property gamma was introduced by Mary von Neumann. So property gamma was introduced by Mary and von Neumann. So this was in the 1930s, 40s, so quite back. Also when they really did their big papers on the basics of von Neumann algebras. And they introduced it as a kind of invariant from von Neumann algebra, and in particular to distinguish the hyperfinite and the free group vector. So in order to distinguish the hyperfinite showed, I mean, the hyperfinite factor has this property, and the free group factor has not this property. So they cannot be isomorphic. If the von Neumann algebra has this property, then any isomorphic also must have this property. Okay, so they showed yes gamma, but the free group factor is not the property. Okay, to show this is not really, it's not too hard. I mean, we could do this and without any reference to free probability theory. Okay. Good, but so I mean, you can also prove this by free probability theory, and that's what I want to show. And maybe first the definition of this property gamma. Okay, so I mean, so we are looking on factors, and this means the center is trivial. Right? So the center are guys which commute with everything. So they are guys from my von Neumann algebra which commute with everything in von Neumann algebra. And of course, I mean, multiples of the unit have this property, but there is nothing else. It's just multiples of the unit. Okay, and I mean, property gamma asks about having things which commute with everything in asymptotic sense. So I mean, if you are in a factor, there's nothing else than multiples of the unit which commute with everything, but you still could have a sequence which, in a limit, commutes with everything. And those are central sequences, and even in a factor you might have such things. So sequence, bounded operator norm, so bounded sequence, let's say tk in our Riemann algebra probability space, also M is a 2-1 factor, let's say, tau is its canonical unique trace. So such a sequence is called central if this sequence asymptotically commutes with every element in if you have for any element in M the commutator of X is Tk goes to 0. When it goes to 0, I mean the norm topology which we are using here is the L2 topology. Not in operator norm, but in L2, because that's a canonical nice norm which we have here. So this goes to 0. If k goes to infinity. Also where it will call, of course, the 2 norm of element y is just tau of y star y in 1/2. That's the canonical L2 norm. If I have a state, or I have here a trace, so it doesn't matter that I put here y star y or y star. Okay, and this of course is the commutator. So x, y, so of course x, y minus y. Also the commutator goes to 0. This means these guys commute asymptotically. And again, of course, there are trivial sequences which do this, namely those which are, let's say, constant multiples of the 1, or even those which are asymptotically multiples of the 1. Okay, so those are always there. So we want to exclude those. So such central sequence is quite trivial. So central sequence Tk is trivial if for k to infinity it is close to a multiple of the identity. So this means again Tk minus power of Tk times 1 and 2 norm goes to 0 if k goes to infinity. Also asymptotically it's just a multiple of the identity. Good. Okay, so those sequences are always there, but now the question is, are there more? Okay, and property gamma means there exist non-trivial central sequences. So we say that in tau has the property gamma. If there exists one more, which is a non-trivial central sequence. Okay, that's the definition. Good. Okay, you can show in the hyperfinite factor, you find such non-central sequences. In particular, if you realize the hyperfinite factor as the group from Riemann algebra corresponding to S infinity. In S infinity, because you have permutations around, and it's easy to construct permutations which give you something like this. Okay, and it's also not too hard to see. Okay, it's not totally obvious, but it can also be done. And that the free group factor has no such central sequences. Good, but we want to prove this now by using this idea here. That the generators of our free group factor are limit of midges. So I want to give you a proof in the sketch of the first part of this theorem, the part on the central sequence. Okay, this sketch is only very rough. I mean, a lot of. Okay, I just give you the outline of the idea, and then when it really starts to get technical, like this. So this is very rough. Okay, so yeah, if we want to show we don't have property gamma, so we assume we have property gamma, and then we have to see that this leads to contribution. Okay, so we assume our von Neumann algebra, which is generated by generators x1 up to xn. I mean, in our case, it will be the free group factor, and this will be, let's say, free semicirculars. Okay, I mean, the idea is more general. So we assume that this has gamma. Good, so this means I have a non-trivial central sequence. So there is non-trivial central sequence, and now I want to improve on this a little bit. I mean, first of all, central sequence, the elements don't have to be self-adjoint, but I can take, of course, the real part and the imaginary part of my sequence. Then again, I have central sequences, and at least one of them is non-trivial. No? Okay, so I can assume that my central sequence consists of self-adjoint elements. Okay, and then I can apply functional calculus to those self-adjoint elements, and I can deform the elements into projections. I mean, I want projections because I can work with those. So by doing this basic things, and this is not really technical, that's standard what I can do. So I can really assume that my central sequence consists of projections. First to the imaginary part. We can assume that dk are self-adjoint. And then I can take functions of those guys. So I mean, dk's are then goes 1 to, so I take a characteristic function of those, and I mean functions of those guys also commute. So they are also central sequences. So functional calculus, we can deform projections. So we're not losing the property that they commute asymptotically, but we make them better. So we have becoming projections, and of course they still they have to stay away from trivial situations. So they should stay away from 0, and they should stay away from 1. Okay. So stay away from 0 and 0 and 1, of course, the trivial projections which commute with everything. Okay, so what we get then from this is, so we have a sequence now a sequence of projections, orthogonal projections. Projections always means orthogonal in our setting, so that we call them now pk. And I want to say that they stay away from 1 and 0, and I can say this in the form that there is a theta, let's say open interval from 0 up to 1/2, such that tau of my tk is bigger than theta for all k and less than 1 minus theta. Okay, so I stay away from 0, I'm not falling below theta. Also, this means this is all k. So I'm staying away from 0, and this means I'm staying away from 1. Okay. And of course, I mean, theta is, tau is faithful, so this will be. Okay, and of course, they are central. So we of course have this condition on the communication. Also we have a sequence of projections and such that we have for all x in our von Neumann algebra the commutator between x and the pk's and the 2 norm goes to 0. So this is true for all x, in particular it's true for our generators. And now we want to argue with the generators because we can approximate the generators now for Neumann algebra by matrices. Okay, so this for all x here means in particular, that's what we are using in following for our generators, which are called x1 up to xn. I assume my von Neumann algebra is generated by those guys. So that's the solution. In our case, we know it's free semicirculars. Okay, good. And now the idea is, that we know that we can approximate x1 and xn by many matrices. Okay, this here tells us we have some conditions on x1 and xn. And we want to see what this means for approximating matrices, and should see a shadow of this condition also for the approximating matrices, and then one should see that this is actually a condition for the matrices which is not satisfied by many matrices. And we know we have many matrices which approximate, so this will be the contradiction. So the main point is to see what does this condition, which we have the limit for in our von Neumann algebra, what does it mean for approximating matrices? If we have approximation in moments. Good. So this is we give you this kind of argument. So this means now we consider matrices which approximate maxes. So now we consider in my n matrices. Let's call it A1 up to n. Approximate our operators in von Neumann algebra x1 up to xn in distribution. So this means we can control, we know something about tau of products of the x's, that this is close to the corresponding trace of the a's. And you see it's good that the central sequence condition is in terms of the 2 norm, because this is a moment. This is talking about moments in those guys. Good. Okay, so we approximate this. So we can approximate the axis, but now of course the condition which we have in the central sequence are those projections. So this means we should also find counterparts of those projections in the matrices. Those projections are in the von Neumann algebra generated by x1 up to xn, which means that they can be approximated by polynomials in the axis. So each of those projections, then projection, let's say pk, m, approximated by polynomials in x1 up to xn. So I want to see what does this condition in the limit actually mean for the a1 up to an, and this condition of course is the condition which involves the pk's. So I also have to find the shadow of this in the matrices. So in the limit, the matrix, the p's, are of course in von Neumann algebra, so they can be approximated by polynomials, and then of course I can apply these polynomials to matrices. Okay, this will not give projections, because they are projections in the limit, but because those guys here are close to this in distribution, if I apply these polynomials here, I can again deform them a little bit. So I can take polynomials, A1 and AN. Okay, so if I apply a polynomial to the axis, I know I get something which is close to a projection. Okay, this means if I apply it to those, I will also get something which is close to a projection, but now I really want a projection, so I should still deform this a little bit to really get a projection. Okay, so I still do functional calculus. And something which is close to a projection can be deformed to be a projection. Deforming result to a projection. Okay, this means I really get a projection here which has properties which are very close to the properties which this projection has here. And of course, one has really technically to control what close means. That's really very part of the whole thing, but in principle, this can be done. So, projection. So the result again to projection. So this gives us then, so this yields counterpart of our projection PK, which was a projection in Neumann algebra. So we find a counterpart of this in the matrices, in the n-line matrices over C. Okay. So what we get? So what we have is a projection we call it QK. So this is the n by n matrix, a projection there, and the trace of this projection is close to the trace which I had here. Of course, the traces in the finite matrices can only, if I take a normalized trace, can only be multiples of 1 over n. So the trace here can be any irrational number, so it's clear I can only approximate this. I cannot have exactly the same. I mean, I'm approximating here everything. So I have to allow small errors everywhere, but these errors can be made as small as I want. Okay, so I have such a projection, such that the trace of QK is close to n times the tau of PK. So the normalized trace of this is close to this, and furthermore, that I also have this smallness of the commutator, and such that. And now I only take the commutators with the generators. In principle, I know, if K goes to infinity, all of them are small, but I just take this for the generators. Because those are the guys which are approximated by the A's. So the commutator between the A and the Q should be close to the commutator between the X and the P, and so this means in particular it will be small, such that the commutator between the AI and the K in 2 norm is small. Let's say smaller than omega k, and this omega k goes to 0 if k goes to infinity, because that's what we know here. So if k goes to infinity, then it goes to 0. So here is k going to 0, k to infinity. And of course, we have this here for all. Okay, now let's see what does this mean. So we have here our matrices such that the commutator with a fixed matrix is small. What does this tell us? Good. Okay, so this, we have here a matrix, and now we go into the basis where this matrix is diagonal. And then we look on this basis, on this matrix, what you can say there. So Qk can be diagonalized. So it's a projection. So this means that eigenvalues are 0 and 1. So if I rotate it as a unitary matrix, it will look like this. The size of this here is of this order. Okay, so those are block matrices. Good. Okay, so in this basis, this Q has a very simple form, and now we also rotate the A's in this basis, and then we check what this condition means for them in this basis. So we rotate the A's. This will just be okay, this will have some blocks which I call BI, CI star, CI, DI. So the A, I assume they are self-short. Okay, so those are just some elements here. Okay. And now this means something for this, and so then let us see what it means. So we have the condition that the commutator between I and Qk, the 2 norm is smaller, omega k, and I mean it doesn't matter in which basis I calculate this. So this will be the same after rotation. So we calculate now this in this basis. And because this has a very simple form, of course this gives us some information about the entries of this 2x2 matrix. Commutator in terms of these entries in 2x2 matrix. So this here means the following. So if I take the commutator of the A, this is the matrix BI, CI star, CI, DI. The commutator of this is this matrix. What is this? So if I take the commutator of this, you see that actually the diagonal guys go away. Because I mean, for this, you get the BI in one order, and you get the BI also the other order. So this cancels away. The same for the BI. So what we get here is actually the matrix where we have 0, 0 here, and the C's survive. Because here we get minus CI star and CI. Because this CI here, well, let's see, if you multiply it in this order, then we get the CI in this order here, but in the other order, this will be 0. Because I mean, this entry here is 0. It will appear if I multiply this from the other side. So the off-diagonal elements will only appear in one of the orders of the commutator. and they will survive. The non-diagonal elements will appear in both products and they will cancel away. Okay, so the commutator is actually this matrix, and the 2 norm of this is now 2 over n trace of Ci star. Okay, and this is small. So this is less than 1 over k. So this tells us, this condition of the commutator tells us that in a basis in which the Q's are diagonal, the off-diagonal elements of my matrix AI are small. Okay, and the point is, it's not only for one of the A's, but it's for all of them at the same time. Of course, I mean, one of the A's, I can also diagonalize one of the A's. And then, of course, the off-diagonal elements are not just small, they are 0. Okay, but if I diagonalize one of them, then the other A's will not be diagonal. Okay, so, and here the point is, I find a basis where I can make simultaneously the off-diagonal elements of all of them small. And this is something which doesn't fit with the fact that we know that we can approximate our A's by Gaussian matrices. Because there it's not true that you can find a basis such that all of them are small. But to put it another way, if we are saying, okay, all those off-diagonal elements are small, it means there are not so many matrices which approximate the A's. Because I have a very specific condition. So I mean, here I have more or less all freedom, but here I have very restricted conditions which say the dimension of the space of elements which approximate this is not the maximum possible. But for our free semicirculars, we know that the space is the maximum possible. There are really a lot of matrices, and this is the contradiction. So this means of diagonals of all the AI in this basis are small. Must be small. Good, okay. But this is not what happens for the GE case. This is not what happens for typical independent GEs, which we know approximate the generators of our phenomena. Good, okay. And of course, this end of proof now should be more the beginning of the proof, because to make this really rigorous, this argument requires a lot of technical work. But at least I hope it gives you the idea. And the technical work is really, I mean, put into a concept which is called free entropy. So, free entropy is somehow a measure for how many matrices we have to approximate a given distribution. Okay, and those here are essentially estimates on the free entropy. Okay. Maybe one other remark here is that, of course, you see that this here I need n bigger than 2, because if I only have one A, then it would only tell me that I have a basis for one A where the off-diagonal elements are small, and that's of course okay. It's of course, it's just if I have 2 or more A's which at the same time can be small in the off-diagonals, then I have a problem. Making one A small is not a problem. Of course, this is what F1, of course, is the commutative phenomenon algebra L of Z, which is very different. And this has property gamma. It's not even, because it's commutative, it's not even a factor. Having not having property gamma means in particular that it has to be a factor. Okay, so maybe let me just make here the remark that technical details are this in the theory of free entropy. And this is handy. The technical details. To make this rigorous. The idea, is quite simple and appealing, I think. Okay, but it really takes quite a bit of work to make these rigorous. So this is more put in a conceptual frame where we have a notion of free entropy. And the free entropy, so it's a free entropy, let's say in our setting it would be the free entropy of the generators of x1 up to xn, and the free entropy is somehow a measure how many matrices do I have for approximating the distribution of x1 up to xn with the distribution of the matrices. Of course, approximate the size of the matrix has to go to infinity, you have to say what approximating means and so on. So it's not an easy concept, but it can be done, and the estimates which you need here is essentially estimates on the free entropy of the corresponding generators. So you have to see that the free entropy actually in this case is minus infinity. So if you have property gamma, the free entropy of the generators must be minus infinity, which means you don't have many matrices which approximate those states. But the argument for showing this is exactly this argument here. That you have constraints on the approximating matrices, which means you cannot have too many. Okay, so and free entropy is still a very active area in free probability theory because there are many problems, technical problems. So, I mean, we have a definition, we have a lot of nice properties about free entropy. We know quite a bit, but it's also there are many things which we don't know, which we would like to know. And I mean, the things which we don't know, if we would know them, then from this we could, for example, get that the free group factors are not isomorphic and things like this. So basic questions are really related with technical problems about the free entropy. And so there's still a lot of work going on in this direction. Good. Okay, so this was this direction. And now I also want to give you maybe another application of this idea, approximating operators by matrices, which goes in a little bit different direction. So this is about the invariant subspace problem. So yeah, I just also want to make a few very general remarks, even less concrete than in this. But this was another case where there was quite some impressive progress, or maybe 10 years ago or so, particularly by which built heavily on tools from free probability theory and this idea of approximating operators by matrices. So let me just say a few words on this. So another result. So this is on hyperinvariant subspaces. So maybe not that we recall. I mean, one of the maybe biggest problems in operator theory is the invariant subspace problem. So this invariant subspace problem. Also, this is about single operators, not about operator algebras. So this invariant subspace problem is asked whether every operator or an operator on the Hilbert space A, B of H, has a non-trivial closed invariant subspace. As invariant subspace, let's say H0. So and what does it mean? Okay, so this means H0 should be a subspace of the Hilbert space. It should be closed, so it is itself the Hilbert space, and it should be invariant under A, which means that if I apply A, elements in H0, I should again land in H0. It means it's invariant. This means if I write, and of course it should be not trivial, of course if I take for H the whole Hilbert space, of course this is invariant, and if I take the smallest possible Hilbert space, namely the one which only contains 0, then this is also invariant. 0 goes to 0. So I don't want this to be the whole Hilbert space, and I don't want this to be just the smallest one. The question is there another non-trivial? And another way of saying this is if I write my operator with respect to the decomposition of the Hilbert space into H0 and its complement, then I can write it again as a 2 by 2 matrix where I have some entries here, and in general I will have entries everywhere. But that this guy is invariant means H0 is swept to H0. There's no component in the orthogonal complement, which means I have a 0 here. But nothing about the rest. The problem is, I mean, in general, this doesn't have to be 0. So I mean, if A is invariant, if H0 is invariant for A, it doesn't mean that it's invariant for A star. Good. Okay, also that's the question whether something always exists, and there's also a 2-1 version of this, namely then it is required that the projection onto this H0 is in the von Neumann algebra generated by A. So this means this decomposition really has something to do with A. It's a kind of function of A, the projections. So that's what is called the hyperinvariant subspace problem, where you require that the projection for this decomposition is really a, let's say, kind of measurable function of A. It is in the von Neumann algebra generated by A. So this means if A lives in the von Neumann algebra, which is realized in the bond operators on the Hilbert space for, let's say, one factor M corresponding hyperinvariant subspace problem asks not only that I find a subspace which is invariant under A, but in addition the projection of the subspace should be in the von Neumann algebra generated by A. So this problem asks also that projection onto the subspace H0 belongs to the von Neumann algebra generated by A, which of course is a sub von Neumann algebra. Okay, so that's the general problem, and actually, I mean, for finite matrices, this is always true. One always has subspaces in B of H. And this is just the reason, because if you have an eigenvalue, then of course you have an invariant subspace. And every matrix has at least one eigenvalue. This is because you can formalize, or you can write a condition for an eigenvalue by a characteristic equation. And you know that you always have at least one solution of this. So this means matrices always have invariant subspaces. It's only a problem in the infinite dimensional case. And then of course, if I have a several joint operator or a normal operator, then the spectral decomposition theorem also tells me that I have invariant subspaces. Because then I can take functional calculus, and then I can take characteristic functions onto something. And so this is also, so this is really a problem for non-normal operators. Operators where I don't have functional calculus. So for matrices and normal operators, it's trivial. The answer is yes, there always exists in my subspace. problem was formulated in a more general context, namely the Banach space context. Now you can ask the same question if you have bounded operators on a Banach space, whether you have something like this. And in this general setting, there are counterexamples. Oh, okay, so this was a famous problem for quite a while, but then there exist counterexamples. Banach spaces. For Banach space versions, same problem. There are famous counterexamples. In the 70s or 80s, so essentially people in my info and by independent info gave maybe the first one, and then he gave maybe easier and nicer versions of this. Good. Okay, so for Hilbert spaces, this is still wide open. And it's one of the big problems in operator theory of Hilbert spaces. So, the problem is thus for operators in Hilbert spaces, and according to this, those are non-normal operators. Also, non-normal operators, which are not so easy to deal with, no? Because we don't have functional calculus, we don't have so many general tools for dealing with non-normal operators. Non-normal operators on Hilbert spaces, or for the hyperinvariant version in a 2-1 factor. Okay, so Ufahagaro made quite some progress on this invariant subspace problem in the hyperinvariant. He did not solve it totally, but I mean he enlarged quite a bit the class for which we know that there are hyperinvariant subspaces. And so the idea was this idea that actually, okay, I mean, if we are now a 2-1 factor and we have our operator, for example, a circular operator. And this is maybe the first nice operator, non-normal operator. If you have a circular operator or an adiagonal operator, which is typically not normal, and one knows one has many matrices which converge to those, but do they have invariant subspaces or not? And this is not a priori a trivial question. There's no easy way to see this, whether we have these hyperinvariant subspaces. But we know that we can approximate them by matrices, and the idea is that maybe we can transport the invariant subspaces from matrices to the limit. So assume, so I'm looking on the operator A, but now I assume that we have matrices, and we know these in many situations, in N, which converging distribution, or the star distribution, is to A. So A is not normal, so I have to look on the star distribution, A and A star, and those matrices are also not normal matrices. Good. Okay, but for each of those for such a matrix, of course, I know that it has hyperinvariant subspaces. Because for matrices, all those things are known. So this AN has invariant subspaces. And of course, corresponding projections, projecting onto the subspace. And now, of course, the hope would be that those projections converge to something. Good. Okay, but in general, there's no reason that they should. Because as I said, the notion of convergence in star distribution is quite weak compared to the usual kind of convergence that you have in operator algebra settings. I mean, if you have the operator norm, then of course you can control very nicely how operators compare if they are close together. If you only know they are close in distribution, then it's much harder to say properties from here that I still have them here or not. Okay, so in general, I mean, it's just not true. Just knowing that this converges in distribution to this doesn't mean anything about the projections which I have here. So in general, in general, those projections might not converge at all. So even not clear to what they should converge in which sense. Good. Okay, but now the idea is that actually, so what we know from our asymptotic freeness results and approximation of theory by random matrices is that we do not only have one sequence of matrices which converges, but we have many. I mean, random matrices means we have a lot of matrices which converge to the same limit. Okay, and so it's not just that we have one sequence of matrices which converges, but which might be very pathological, and the problems of this matrix might not have much to do with the properties in the limit, but if we take many of them, if we not take, let's say, a random matrix or formula which converges, then maybe generic properties should at least go over to the limit. So we should improve on this convergence, on this situation. Now we improve the situation by going over essentially to random matrix with formula A n prime. Then we take a n, but we are adding a small perturbation by Gaussian matrices. So we are adding, let's say, epsilon n times xn. Where the xn here are non-self-adjoint Gaussian unitary matrices, GUDs. If epsilon n goes to 0 in the limit, then actually the star distribution of those guys in the limit is the same as the star distribution here. So we get here suddenly much more matrices which converge to the same limit. And then there is at least more hope. You also can save something to the limit. So this xn non-self-adjoint GUEs, so GUEs which have no symmetric condition, and this epsilon n goes to 0 in the limit. And then we still have the convergence in the star distribution, so we still have, so we have not destroyed the nice thing which we had at the beginning, namely a n prime converges to a in star distribution, and this happens now almost surely. So always means it almost surely, but not just an average, but it actually for almost surely all matrices which I have in this ensemble, I have this convergence. So this happens almost surely. And so now instead of just one sequence of matrices which converges to A, I have many sequences. So we have many sequences. Matrices converging to our limit operator. Okay, and so and it's really possible to control somehow the generic behavior of those. Okay, but again, this is now it really starts to become very tough and technical, and so we have no chance of doing more details about this. Okay, but in this setting, it really can be shown that generic behavior of these matrices goes over to the limit. Okay. This means one can, at least under some conditions, one can get hyperinvariant subspaces to the limit. Okay, and so I mean, in the end, one has the following result on this. I just want to give you the result, which actually was not done by a random matrix ideas, but by some other approach, but which still used a lot of free probability theory. I mean, one problem here is that if you start with an operator, you have to know that there exists at least one sequence of matrices which converges to this guy. And we don't know this. I mean, this is another problem, Const embedding problem, operator theory, which asks exactly this. Is it true that any operator can be approximated by matrices? I mean, of course, we know. The operators interesting for us, semicirculars, free semicirculars, they can be approximated. But if we just take any operator in some maybe strange from Neumann algebra out there, we don't really know whether we can construct matrices which do this. So this means, I mean, this idea here would only apply to operators which can be approximated by matrices. Okay, so Agaruk did another approach which avoids this, which is true for any operators. But still, I mean, uses a lot of ideas coming from this. And maybe I give you the theorem, just to give you kind of idea. So this is by Agaruk and Anne Schulz from 2009. At least that's when it appeared in the end. I mean, this whole idea, starting from this, I mean, this idea started at the beginning of 2000, and it took maybe quite a while until I got this final application. So what is the statement? So if A is an operator in general to one factor n, then essentially one can make a decomposition like this for any subset of the spectrum of the operator. Or actually for any decomposition of the complex plane into a Borel subset and its complement. For every B, C, there is a unique closed A invariant. Okay, it's invariant with respect to A. Invariant subspace. The problem is here that I'm not saying trivial. No? It might be, it could be trivial. No? So if I would say non-trivial, then it would be solved in generality. No? We have decompositions, but we still have to check whether this gives us non-trivial subspaces. Okay, let me first say it like this. There's a unique closed invariant A invariant subspace, let's say K, which is affiliated to M, which means that the projection onto the subspace belongs to the von Neumann algebra. With respect to this, so I'm writing my operator in this form, E22. But now, okay, I have some more conditions, some statements, such that actually what is called the Brown measure measures of A11 and A22 of this guy and of this guy are concentrated on B and on the complement C. Okay, I don't know what the Brown measure is. This is a generalization of the distribution of an operator. I mean, distribution of an operator, what we call UA. UA, but we only had this for normal operators. Okay. So they have a joint for normal. And then this is a probability measure living on the spectrum of A, which captures all information about the star movements. One can also define this in general, but if A is not normal, then I mean it's okay. Then I have the problem that I cannot really associate the star moments of A to the moments of a probability still one can define a measure which captures part of the information of the star moments. Okay, so there is something which is called a Brown measure, and I mean a lot of the work of Hagerup was also to revive the theory of the Brown measure. Okay, so there is something called a Brown measure, and this here is telling me that actually, I mean, this guy has a Brown measure, so this is a measure which lives on the spectrum of this guy, and this decomposition respects somehow the Brown measure. So this part of the operator gets the restriction of the Brown measure to the set B, and this part of the in this decomposition gets the part of the Brown measure which lives on the remaining part. Okay, and now if there is a Brown measure which I can decompose into two parts, then this tells me that those guys are not trivial. So I mean, if I state it like this, I'm not saying that those subspaces are not trivial. So it might be that those guys are actually empty, and then I don't have a solution to the hyperinvariant subspace problem. But if I have reasons to tell me that those guys are not trivial, then I really have a solution to the hyperinvariant subspace problem. And so if the Brown measure of this operator is not a delta measure, then I can decompose this Brown measure into two parts, and I get a corresponding decomposition of my operator into this, to my two matrix situation, and this guy has a Brown measure, and this guy has a Brown measure, which tells me that they are not trivial. And then I have a non-trivial situation. Okay, so the final result on this is, so in particular, if the Brown measure of A, my operator A, is not a Dirac measure. So this means A is something which I can decompose into two parts. Then I get here non-trivial decomposition, and then this means that A has a non-trivial hyperinvariant closed subspace. Okay, so this doesn't solve the problem in full generality, because there are many operators which have a Dirac measure as its Brown measure. Also, there are triangular operators or things like this. So there are quite a bit of operators which have this Dirac measure. But of course, there's also a big class of operators whose Brown measure is not a Dirac measure, and then this tells us there's always a hyperinvariant subspace. For example, the circular operator or all other diagonal operators, they have hyperinvariant subspaces. I mean, this was proved before by direct attack on this specific class of operators, but all this is summarized, taken over by this very general theory. So this tells us for big classes of operators, in order to get hyperinvariant subspaces. Good, okay, but I mean, technical details of this are very tough, so I don't want to go into this. I just want to give you an idea that free probability, and in particular this idea that we can approximate operators by matrices, really resulted in quite a bit of progress on quite important problems in the operator theory and operator algebras. Good. Okay, but so I think that's what I wanted to tell you about free probability theory. So we have seen, I hope, summary of what free probability is and what it can do, and also how it can be used for operator algebras, but also how it can be used for dealing with random matrices. And so maybe let me close by saying that next term I want to give another class which is in some sense a continuation of this, but on the other hand it's also kind of independent. So this will be called non-commutative distributions, where we will look maybe more on distributions of operators, regularity properties and things like this. Again, by using free probability theory. And in particular, content will be that we do actually an operator version of free probability theory. So we will lift the whole theory to a higher level, which is formally very similar, but technical details are harder, particularly analytic theory, but it still can be done. And this theory is even useful for dealing with problems which are somehow left open in this theory. So what we talked about here was, from an analytic point of view, of describing really free variables, was that we understand how to deal with the sum of free variables. That's the convolution, the free convolution. We derive analytic machinery for calculating the distribution of the sum of free variables. But of course, if I have variables and the distribution of them is not just done by taking the sum, if I have a tuple of operators, the distribution is by looking on all polynomials in them. And I want to understand the distribution of all polynomials in them. And up to now, we have not really addressed this. We know in principle everything is determined, but a good analytic tool for really calculating things you only have for the sum. And then next term, you will see that actually by using sums from the operator value theory, we will be able to deal with polynomials in this scalar value theory. Okay, so maybe I hope that we see again next term. Okay, that's it. Thank you.